Welcome to Walkabout the Galaxy, the topsy-turvy astronomy podcast where the science is universal, the opinions are personal, and the points don't matter.
But I still win.
What happened?
What are these fans going?
Oh, maybe. If you put your headphones over both ears, you won't hear it anymore.
I don't like having my headphones on both ears. Smushes my head.
We are Strange Charm, top and down the astroquarks, also known as Josh Caldwell.
Patty Dove.
Jim Cooney.
And Audrey Martin.
Coming to you from the Walkabout studio at the University of Central Florida with 3 real quarks and 1 virtual quark. Be sure to follow us on Instagram. Instagram.
Are you okay?
I'm choking up on Instagram.
Aww.
And anywhere else we may happen to show up, but mainly Instagram, where the facts aren't checked, but you can always trust the astroquarks.
Yeah.
Yeah.
Really?
Usually.
Yeah. Catch our videos on YouTube. We are at Walkabout the Galaxy. You can email us at wtg@ucf.edu. Our stumper today is instrumental.
Okay.
You get to send one and only one instrument on a planetary mission to the Centaur object Charon, about which we'll be talking a little bit later.
Mm-hmm.
In the outer solar system, has not been visited by a spacecraft and no plans to do so in the near future, but you can only send one instrument there, and you have the following 4 choices.
Oh, damn. Okay.
A visible camera, visible light camera, an infrared spectrometer. You choose your resolution and spectral range as you see fit. A cosmic dust analyzer, so something that can detect dust impacts and measure their composition and charge. Or an ion and neutral mass spectrometer. What are you going with?
That's tough.
Ah!
It's got to be either the imager or the dust analyzer.
Cosmic dust analyzer, or the visible light imager. Yeah.
I think it has to be the imager. If it's only one,
Just got to have pictures.
You have to have pictures.
Yeah.
Yeah. It has. Yeah.
Okay.
Got to be.
What was the second? There was a
infrared
visible,
spectrometer.
Infrared, dust, and ion and neutral. I'm going to go ion and neutral.
Nice. Fields and particles. Threw that in there just for you, Addie.
Thanks. I mean, between dust and fields and particles,
Right.
we might shock the listeners that I picked
That's
fields
true.
and particles instead
That's
of
true.
dust.
Yep. So,
Are you shocked, listeners?
Jim?
Got to be the IR spectrum thing.
Oh, that's you're just.
I'm doing that partly
getting
to,
points with your wife.
Yeah, ingratiate. Yeah, because my wife does that.
Well,
but
that's
also, it's indicative of fun things on the surface, like organics and whatever. You can learn cool things.
Can you?
Yeah. Yep.
I don't know.
Yep.
I don't know.
So she tells you.
That's what I'm told.
Yeah.
Yeah.
I think I got to go with the imager too. It's kind of the safe, maybe not as interesting choice. It's not as a surprising choice,
The
right?
instrument isn't interesting necessarily.
It's just gonna be. It's gonna look like a potato with a bunch of.
But there, as we will learn, there's things coming off it, and this is not just a flyby; it's an orbiter. If that changes anybody's answers in this imaginary mission,
Sure.
and so
You can
there's-
map the whole surface. And in this
that part
scenario,
is I agree with Jim. It's like
to
if it was only the
sub-centimeter
surface,
scale.
if it was only the surface and it was not like whatever, it's like, okay, it's going to look like a battered potato, right?
Yeah. I mean, those are
But-
cool images. I've seen, you see a million pictures of all these asteroids that we've been to. They're really cool. But once you've seen a few of them,
Yeah. But because this thing is
I call
active,
BS.
there's
It'll
stuff coming
change.
off it.
You'll see stuff flying off.
You'll see where it's coming from. You'll see what the
Can we all make arguments that are this long for our instruments?
sure.
I just kidding.
Let's hear your long argument for the
Actually,
ion and neutral mass
Can't
spectrometer.
wait. So actually, during the journal club we had today, which was talking about cometary activity and active asteroid outbursty type of things, right? One of the super interesting things is being able to see when different species come off, and they track some of those maybe to a failure on the asteroid because it's it gets activated by going near Jupiter and having
right.
a collapse or something.
You could see that
happens.
collapse with an imager.
You could
Right.
see it with an imager. They detected it with their instrument, but then they detected this other thing with the instrument that the imager didn't see. And it turns out it was because it was a CME hitting and creating all of the
Coronal mass ejection.
high energy stuff hitting and creating additional information that they couldn't get with the imager.
Okay. Well, a true stumper. Today we'll talk about Chiron a little bit, the formation of Pluto's moon Charon, the larger moon. We talked about the smaller moons previously, so we'll put some new info into that context, that whole thing, and much more. But first, this episode of Walkabout the Galaxy is brought to you by, amazing that this has not been a sponsor before, Dark Energy.
Wow. They must have heard us. Their ears were burning recently.
Even if you know the power of the dark side of the Force, you still don't know the power of dark energy. Able to expand the entire universe, dark energy is darker than dark matter, more sinister than the Sith, and more mysterious than what your partner really wants from you. Accounting for 2/3 of all the energy in the universe, dark energy can handle all your chores with room to spare. If you need to blow up your world and get literally clear space out, literally clear space out, not can get literally clear space out, get your act together, dark energy.
Yeah. That wasn't anyone but dark energy that did that.
It was definitely, I just read the copy dark energy sends me.
Maybe you read it wrong.
No, it does say get literally clear space out.
That probably makes sense with some
you just have to think about how dark energy means it.
Yeah, I think that dark energy, when they were sending this to me, was like a little bit confused about what exactly they were going to say, and they didn't write exactly the right thing.
Yeah, that's okay.
And I'd have to just read what the sponsor sends me.
That's right.
Yep. I can't, edit
There's no ad-libbing
right.
in this sponsor messaging.
Mm-mm.
If you need, so as they said, if you need to blow up your world and get literally clear space out, make room for yourself with dark energy, the reliable one. Oh, you're all going to get it.
Really?
Aren't you?
The reliable one?
OUC.
That's right.
Orlando Utility Commission, the reliable one.
Yeah.
You might not have OUC.
I don't have OUC, but I still know that that's the reliable one.
Reliable one.
That's
I
the
do
local,
have OUC.
The local power company here.
Oh.
Yeah.
Okay.
Anyway.
I got it. Jim, would you have gotten it?
I don't think. I mean, now that you say it, I'm like, yeah, of course, but I wouldn't have got it.
Huh. I hear OUC, the reliable one, all the time.
I think that's because we listen to NPR.
Yeah.
Oh, yeah, I don't.
Okay. Space news. Last time we said that maybe before the next episode, in other words, the previous episode airs, we would have the launch of Starship Flight 7 and New Glenn Flight 1.
Nope.
I think I just said Flight. Now we're going to say the same thing again this time. Maybe before the next episode airs, those two flights will happen. They're
concurrent with this episode airing for the Firefly one.
Oh.
We didn't even mention Firefly.
So what is
Firefly's first? We did talk a bunch about Firefly the last time because Blue Ghost 3 mission is the one that Lunarvise is going to be on. Mm-hmm. But the Blue Ghost 1 mission is launching on a SpaceX vehicle.
When?
Next Wednesday.
Cool.
February 15th. And it's the one that
January
has not
15th?
only, yes, thank you, January 15th. It's the one that has not only the Firefly vehicle, but the iSpace lander also. So there are two lunar landers on the same vehicle. And they're taking very different trajectories to get to the moon, so they get there at very different times. Super fun.
Oh, that's
Orbital
exciting.
Dynamics. You can sponsor us again soon.
Yeah.
Sure. And the new...
So that's scheduled for January 15th.
Yep.
New Glenn 1 is scheduled for a little over 24 hours from now as we're recording this.
Oh. You want to go out? It's at 1 a.m. on Saturday night.
Maybe?
Yeah, it'll be super fun.
1 a.m.
Like Sunday morning.
Got it.
Yeah.
Yeah.
Okay.
It's going to be so cool.
SpaceX Flight Test 7, Super Heavy Flight Test 7 Starship is scheduled maybe a day or two after that.
Time.
So, yeah. One of these days, we'll be reporting those things in the past, not in the future.
One day.
Last time, I think Jim told us had a speed trivia that referenced the Parker Solar Probe, which I don't think we talked much about it, but it made its closest flyby of the sun at a distance
That's why we were doing it.
of 3.8 million miles above the photosphere. And it survived.
How fast? How close was it the last time it did the flyby? Because it's done a few flybys now.
Not much further than that.
Okay, that's what I thought.
Yeah, it's doing a total of 24 or something like that.
And have we crashed things into the sun?
Oh, that's a really interesting
question. Because a bunch
question.
of the articles I saw said closest we've ever sent any human-made spacecraft to the sun. And I was like, I'm pretty sure like things have crashed into the sun.
That's what I thought. Like if you have a mission...
I'm not sure.
You have to either crash
I am
into
not
the sun
aware
or
of
burn up in
anything
the
that we've crashed
atmosphere.
into the sun. That doesn't mean we haven't.
Or burn
I've never
up in
heard of that.
Saturn.
What did you say, Audrey?
Like you need a death plan for missions.
You just put them in a stupid orbit that's never going to hit anything important.
Oh.
Yeah. As long as you're sure it's not
dark in space.
As long as you're sure it's not going to hit like Mars or Europa. then
Oh,
it
so
doesn't really
nothing
matter.
Lifey or potentially lifey
Right.
or past lifey.
Right.
Oh.
Messenger plunged into Mercury. That was the other thing that was kind of close, but it was
Yeah.
at Mercury.
I don't know of anything that has crashed into the sun. It's not. It's not. It's harder than it sounds.
Sure.
Actually.
Is it? You'd think just like
Yes.
drop it and it would go,
Right.
but nope.
No.
Yep. You have to have it lose all of the energy that it's got from the Earth's motion around the sun, which is a fair amount.
Oh, no.
So we're
I
zipping
think the
along.
mission Icarus would have.
You have to like basically think about shooting it with the Earth's orbital velocity in the opposite direction for it to
Right.
drop in a straight line into the sun. Right.
I think that's a great idea.
We're going 30 kilometers per second this way. Your spacecraft would have to go 30 kilometers per second in the opposite direction. That's actually really fast. So, yeah.
Orbital dynamics, man.
Yeah. So
Again,
anyhow, it's worked
so
its way down
crazy.
there and it survived. We don't have results yet, but one thing we should maybe mention, I'll mention it
We're
whether
gonna
we should or not,
Yeah.
is one of the things it's trying to do by flying in that region. It's basically in the solar corona. It's the part of the sun that you see during a solar eclipse, for example. And one of the weird things about the sun, and
It's hot.
it's hotter than what's below it.
Yeah.
Which is weird. So
that is
something
weird. We
heats
don't
up
know.
that gas. And we're trying
Energy.
to figure out what that is. It's not dark energy. It's some other kind of thing. So, yeah. So that's what, the sort of, in a nutshell, one of the main science questions is, what is it that makes the solar corona millions of Kelvin, whereas the solar photosphere is only thousands? It's like as you go from
that much hotter.
yeah, as
Oh
you
my
go
God.
from the center of the sun outwards, the temperature goes down, 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 down to the photosphere. That's what we see. And then this rarefied atmosphere is superheated. So there's all sorts of ideas
But
about
you gotta be,
the
I
heating
mean,
mechanism.
it's not quite as weird as it sounds.
Oh,
I mean, it's
yes,
weird,
it
And I
is.
think it's not well understood, but it's not as weird because it is very, very, very thin compared to the photosphere.
Right.
Like,
there's less
it's
energy.
a handful of
There's
particles.
less energy there,
Right.
but something has to energize that stuff.
Or there's less stuff there.
Yeah.
It's
So,
very
like-
wispy. I mean, that's why you don't see it, right? I mean,
The Earth's atmosphere does, the planetary
Yeah.
atmospheres do the same thing. They're hot at the bottom because the surface heats it up, and then it cools off, but then it gets hot at the top
Yeah.
because the sun is heating it at
Yeah.
the top, right? But there is no sun to heat the top of the the sun. The sun is at the bottom. It's not at the top, right?
right.
I think that's clear as
Clear as the photosphere.
there you go.
Oh, that even rhymed.
Any other space news that you would like to share?
I feel so like that. Yeah.
Yeah.
I feel like there is.
Well, one of our colleagues.
I feel like I had a nerd news,
Oh,
but I am blanking out what it was. I was
One of our-
watching some show recently.
that's good stuff.
I watched a show recently too.
Yeah.
Did you?
I have seen a show once in the 80s.
Was it a science nerdy show?
No. RuPaul's Drag Race.
Oh, yeah.
So, one of our colleagues, Charles Chambeau, is he the lead author on this paper about Chiron?
I think it's Noemi
Noemi
Pena Alonso.
our colleague, formerly here at UCF, has now moved back to Spain, has a new paper about Chiron, the Centaur destination of our Stumper mission.
Yeah.
So
Remind us what a centaur is again?
a centaur is an object that is crossing the orbit of one or more giant planets, and it's beyond the orbit of Jupiter. So it's sort of in between Jupiter and Neptune. So these are believed to be kind of transitional objects from the Kuiper Belt moving in as comets. So it's not a huge population. In fact, Chiron was the first one of these objects to be discovered, first object to be discovered on this kind of orbit in, anyone care to take a guess or know the answer?
1977.
That is correct.
I read that earlier.
Cheater.
So,
Educated on the topic. What?
yeah.
I know. Pretty special.
So it's a population that's relatively recently discovered.
It's older than
the
both
Kuiper Belt
me and Audrey
in terms of
in
discoveries.
terms of discoveries. Yeah.
Yeah. Okay. And but even now, we don't know a huge number of objects in that region because their
Right.
their orbits are unstable. They're constantly being perturbed by the giant planets, and so they end up getting pushed onto a different orbit, either a cometary orbit or ejected from the solar system, perhaps.
And they're kind of small and kind of dark. And they're far away. And it's hard to detect
hard to see.
things
Hard
that
to
are
detect them at all.
Yeah.
But I think we know of many, many more trans-Neptunian objects than we do of Centaurs.
Oh, yeah, definitely.
And that's because those guys are lasting for billions of years, and the Centaurs are lasting for less than billions of years.
And by lasting, we don't mean that like the body itself disintegrates.
Right.
It's like there's this big question of like, what are these populations, and they interchange with each other, and so it's not in the same like orbital dynamics to be a centaur.
Right.
Yeah.
So what does Noemi and Charles's paper tell us about Chiron?
So they had time on the JWST the space telescope,
Nice.
old twist. And they looked at Chiron. So a lot of centaurs have cometary activity, and it's very confusing, and a lot of it is very unknown because they're far away from the sun. Whenever we observe comets that have tails, it's when they come very close to the sun. But centaurs in their orbits never come that close to the sun.
Right.
And so there's a big question on why
where's that tail coming from?
Where does it coming from? What's going on there? And so they have some spectra of Chiron during a period of activity. And what's really cool is that they're able to not only detect the material and know the material that's in the tail, but also what's on the surface as well.
So they're able to separate those two components.
They're able to separate it out.
So just as a refresher, we see the tail on a regular comet when it comes close to the sun just because that heats it up. And the tail is mostly driven by evaporation.
Yeah.
So you have ices and you heat it up, stuff evaporates. This stuff is super, super cold out there.
Yeah.
Where that isn't normally happening.
Yeah,
right?
you wouldn't expect that to happen, but it is happening.
And so our previous observations, we've seen something about composition, but have not been able to tell whether we're looking at the tail or the body.
Yes.
Okay.
Yeah.
And now we can separate, and what do we see?
And with a lot of comets, when we're looking at them too, the coma is much denser.
Yeah.
Right? So
it's much denser and it's much brighter than the comet itself.
For Chiron.
No, just in general. When you're looking at comets, right? Like
yeah.
you can't see the surface of the comet as well, and at the same time as it's being active, because when it's
all the
active,
stuff around
it's
it blocks your view of the thing in the
But with
underneath.
this one, because they're able to resolve it,
I see.
and because it's like a lower density thing, they can really distinguish the characteristics of the coma and
I see.
the body.
Yeah. So there's, I think, going to be a lot of follow-up work on that, but the big detection is being able to separate it out.
Okay.
So what's the coma made of? What
What is it?
What is
So
sublimating or
they
evaporating
see-
or whatever off the surface of a thing that far out? Because my astronomy
see-
101 understanding is like 5-ish AU is where things start to
Yeah.
come
Yeah.
off. But these are past that. So what's
So they
happening?
see carbon dioxide and carbon monoxide ice as what on the surface, and then carbon dioxide and methane gases in the coma.
Yeah. And those are much more volatile than water, so they evaporate at lower temperatures.
Carbon monoxide evaporates.
That's the crazy
really
volatile one.
far out, because
Yeah.
we were doing like this little
Those
comet
models
modeling
long
thing for a
ago.
while, and
Yeah.
I was like, it's
Can't
always
get it
just
to work.
it's like 8 or 10 AU. It's like gone, and then or maybe it's really far out that it like starts
Yeah.
evaporating.
If you look at like the evaporation rate or sublimation rate, it's exponential with temperature. So it's like really kind
It
of
just
turns on.
Yeah, there's like a
And
switch.
it turns on for CO at a very low temperature.
Interesting.
Yeah.
But this is similar to, so I think we talked about a previous study from Noemi and Brittany Harbison, one of her students who had looked at other trans-Neptunian objects and found like what sort of chemicals are on the surface, which is like what we're really being able to do with JWST.
Yeah.
And it's sort of a comet asteroid hybrid.
And one of the weird things about
Yeah.
Chiron with this stuff coming off is some of the stuff that's been observed around it has been at least discussed in the same conversation as the rings that have been discovered around some other centaurs
Always bringing
and
it back to
trans-Neptunian
rings.
objects. You know, always circle back.
Always. Yeah.
So cool. That's why I would want my imager to go to Chiron.
Oh.
So Charles mostly does, or he does a lot of like modeling too, to understand like where you get heating and how that would cause the evaporation. And so the other part of it is determining that probably the gas is consistent with the area that is the most heating from the sun. So it's probably like the subsolar point that's getting the most heating, and that's where the sort of flowing gas is outflowing from.
Okay. So it is driven by the sun.
Effect.
Yeah. Because the other possibilities could be like it gets impacted by something or some other thing. So so that's a discovery. Well, speaking of things that start CH and end RON,
yep.
Pluto's moon
Charon. I was just putting a different
Charon.
Charon would be tasty. Ooh. It would be cinnamon sugary.
Dipped in chocolate.
Like a churro.
Okay.
Charon.
Pluto's largest moon is interesting because if you compare the size of Pluto and this moon, the ratio is much. The moon is much larger compared to the planet than any other system like that in the solar system.
Most. Maybe.
Isn't it like a 2-to-1 or something in diameter?
Yeah. The diameter ratio is just a factor of 2. Mm-hmm. So like the Earth is 4 times bigger than the moon in diameter, and the mass goes as the size cubed, and the moon is significantly less dense than the Earth. So in any event, it's kind of referred to as a double planet. Like the moon always keeps the same face to the Earth. Mm-hmm. Charon keeps the same face to Pluto, but Pluto also keeps the same face to Charon.
So they're just staring at each other.
They're mutually tidally locked. So the question of how you form that moon has been a question that's been studied for a long time. And you know how we planetary scientists are when we have a stumpy kind of question like that. We're like, must have been a giant impact, you know. And so that's like how our moon formed. It's like something Mars-sized smacked into the Earth and obliterated things and made a giant disk, and the moon formed. But out there, where Pluto is, those collisions would be much slower. Mm-hmm. And the objects are much smaller than the Earth and whatever it is that hit the Earth. Mm-hmm. So their gravitational self-binding energy is much smaller. So it's a different kind of regime, and that hadn't really been considered before. So these researchers basically did a more sophisticated numerical simulation of the collisional formation of Charon, and they found they could make it in something they call a
kiss and capture.
Thank you.
Kiss and capture.
Aww.
We've talked about those before, I think.
That's very sweet.
Yeah.
So it comes in as a sort of glancing collision, but the objects have instead of the previous simulations always just assumed, I don't care about what the strength of the object is because the gravity of it overwhelms the strength. Mm-hmm. Here, that's not the case. They're smaller, so the gravity is weaker. And it's like, let's put the strength of the thing itself into the simulation instead of just considering it a strengthless blob of fluid in our computer simulation.
I feel a lot of times
as a strengthless blob of fluid. It's Friday afternoon, and I'm totally in the strengthless blob of fluid. Yeah. And I don't have a lot of self-gravity acting right now either. So anyway, so they put that material strength into the objects, and that gave them this sort of kiss and capture where the impacting sort of proto-Charon comes in grazing collision with Pluto, and it's not a big disruption event that makes a big disk. They just sort of like stay in contact for like 10 hours, like 3 rotations around, and then the Charon sort of naturally separates away from a spinning object, and then there's tidal evolution that takes it out to where it goes. What's the
dynamical stability of Charon's current orbit?
Très stable. I don't know why I went to French, but yes.
Okay. Très stable.
Yes. I'm a strengthless blob.
It's pretty stable.
Yeah.
Like,
it's a circular
so like our
orbit.
moon is receding at centimeters per year. Is Charon moving in or out?
It is receding.
Distance per year?
Yes.
Okay.
There is some number associated with that.
But it's not.
I don't know the number.
Okay.
Yeah.
But it's on the order of like tens of thousands of years or hundreds of thousands of years stable, not like millions of years stable, not like hundreds of years stable.
Yes, it's definitely it's not going, it's as stable as our system dynamically.
Oh, that's nice.
Yeah.
So good for them.
Their relationship is stable.
Yes.
Yeah. And so they're suggesting maybe they need to go back and take a look at some of these previous simulations that have been done for other giant collision scenarios and put the material strength as well as the gravity.
It's crazy
into those
that nobody's
things.
ever thought of that.
Yeah,
I mean, they
well,
have thought of that. It's
you
just
think
really
of it.
computationally.
Yeah, that's what
Yeah,
they were
it's hard
saying,
to
that
do.
they were able to get like supercomputer time.
Yeah.
I did some collision stuff like this back in the 80s and 90s. And
Oh, did you do it by hand?
yeah, right. No,
While,
I
were you
used-
doing it while
like, come on.
beatboxing?
I used an abacus.
Oh.
Mostly just
great.
throwing Play-Doh and other
And
pieces
a
of Play-Doh
slide,
and see what
an
happens.
abacus and a slide
Don't tell
rule.
our secrets, Jim.
But you can take like what's the gravitational binding energy of an object, and that increases quite rapidly with size. And then there's like what's the strength of rock, and it's kind of just this number.
Yeah.
So
And I
once-
always use like dolomite or some rock value in most of the simulations.
Yeah.
Dolomite?
I don't know.
Why?
So it's like
They
once you're
do.
bigger than a
Probably
certain
average, like-
size, the gravitational binding energy for the thing as a whole is orders of magnitude more important than the material strength. And what I was looking at was like, what does it take to break up a moon to make a planetary ring? And if the moon is bigger than like 10 kilometers, I don't care. I only care about gravity. I don't care how strong it is because gravity is the dominant thing. But here you're looking at the details of all the little pieces in that
Right.
collision. And so you have to consider that strength as well. So it gives us, and they have a very nice little movie of the kiss and capture.
I'm sure they
Yeah.
do.
Aw.
Yeah. It's very PG.
Oh, good.
Yeah. All right. Well, speaking of things spinning around, which we were a little bit there, that's what our trivia is. Then we'll move out into the broader universe as a whole.
Wow.
So, yeah, we
Oh,
got
we lost
everything
him.
covered here.
The whole
We
universe.
started like with the sun, and then we're moving out to
Yeah.
the Kuiper belt, no, to the Centaur orbits, and then Pluto. Our trivia has to do with how fast things spin. What is the period of the fastest spinning pulsar? If you were on the equator of that pulsar, how fast would you be moving due to the rotation of that pulsar? What is the period of the fastest spinning asteroid? And for the planets in our solar system, how fast would you be going on the equator of the fastest moving equator in the solar system? And how fast would you be going on the slowest? And which is the slowest?
Will this
I'll come back to all
exam
these
be,
questions. We'll come back to
part
all
of my
these
grade?
questions. It will be graded. Yeah. But remember that the points don't matter.
Oh, thank God.
Yeah. That was at the intro if you were paying attention. You weren't. So
Well, I'm not being
1,000
graded,
points
so.
off.
Thank you.
1,000 points off. But the points don't matter. Our sponsor was Dark Energy, Jim. Should they get their money back?
No, we're good.
We're good. Okay.
Don't worry.
All right.
I was
That was a
getting
very
nervous.
suspenseful pause.
It was.
Yeah.
Yeah. Mostly because I think my internet connection is crap. But
I think it is
you're
too.
you're very but blurry over there.
Yes.
I'm sorry. I don't know what's going on.
Jim has become a 1970s CRT show instead of an HD cinematic experience.
Well, that probably improves how I look. So
No.
we'll stay with that.
Your words. Oh, jeepers. That's bad timing.
Well, he just
Energy.
didn't find it funny at all.
Yeah.
So
Jim, we need to do something about Vermont's internet connection.
I know. It's probably getting bogged down in all the snow
happening?
they're having up there.
Oh, yeah.
Yeah.
We're filling time.
We're filling
until your
time
internet
because
comes back,
we're
Jim.
getting one. You remember the old modem dial-up connections? That's what we've got with Top Quark Jim Cooney right now. Yeah.
Ding,
All right.
ding. What were we going to talk about with Jim?
We were going to
Dark
talk
effect?
about whether dark energy exists or not.
Oh, yeah.
Let's just say it doesn't. Come on.
Oh, no.
Yeah.
Nuts.
Let me give you two the since there were multiple parts in
Wow.
the
This
trivia.
episode is a special episode.
It's a special episode. I'm going to give you the first part of the trivia.
Okay.
Okay.
What is the period of the fastest spinning pulsar? Pulsar is a rapidly spinning neutron star. So how long does it take to rotate once would be the period. Pulsars, they're like 10, 20 kilometers in diameter. So like the size of a town, mass of a star. And some of them can spin fast, but, that's still 10 or 20 kilometers. It's got to take some time to go around.
Yeah,
Right?
it can't be.
Yeah.
Yeah. So how fast is the fastest spinning pulsar spinning around?
I see a Jim.
Ooh.
Oh,
That's you.
Jim,
Am I back?
You're back.
You seem to be back, but we're filling the dead space with the answer to the pulsar question on the trivia. Then we'll come back to your dark energy if you're still there.
Yeah.
okay.
Period of the fastest spinning pulsar. Addie Dove says
7.
Audrey says
1/10 of a second.
0.1 seconds. Jim says
1,000 times a second. So a 1/1000th of a second.
1 millisecond. Do you want to put units on yours now, Addie?
Nope.
She's going to stick with 7. Even unitless, Jim wins
Okay.
because it's 1.4 milliseconds.
Okay.
Yeah. 700 and some
So
hertz.
fast.
How fast?
1.4. So I was only half off because I.
That's true.
So
That's true. That's,
My units were
I
milliseconds,
wasn't thinking about it
so-
that way.
Yeah.
But yeah, if your units were 1/10 of a millisecond or something.
Yep.
So you get 7 points.
Thanks.
If you were on the equator of that pulsar, how fast would you be going?
I can't do that in my head.
Well, if you could, then it wouldn't be trivia, it'd just be a calculation.
Sometimes trivia is just a calculation.
It is, yeah, but this was meant to be answered more quickly than you can do the calculation. Although I can see Jim has got his calculator
No,
out.
he's got his
I don't
abacus
know.
out.
Yeah.
Million miles an hour.
50,000 kilometers per second.
Jim?
96% the speed of light.
I think Addie gets this, actually. 50,000 kilometers per second.
Kilometers per second.
And speed of light is 300,000, right? So you said 16% the speed of light, and the answer is 24% the speed of light. So that's remarkably good.
Wow.
7
Yeah.
more points.
I love that we
Very
all
good.
use different units.
Yes.
Too.
Yeah. I didn't bother converting yours, but hers was so close.
fine.
I'm like, she wins. Yeah. Okay. Now, Jim, that you're back in the world, you are aware this is the 21st century, right? And we do have this.
Vermont might not be.
We do have this thing called the internet that,
I don't know what happened there.
Your
I don't know.
AOL
I'm blaming it
dial-up.
on you guys. Wasn't my fault.
all right, dark energy.
Dark energy. We know it. We love it. It's as the
Do we
sponsor
know
message
it?
said.
Do we love it?
We don't know it.
I actually don't know it, and we probably don't love it.
Right.
But we think it makes up something like 2/3 of the energy budget for the universe. This is originally was based on
That's what the
measurements
sponsor
of
said
how
anyway.
quickly supernova are moving away from us back in the 1990s, and they won a Nobel Prize for this discovery and everything like this. And it's one of the hallmarks of our basic model for cosmologies.
Oh, is there a Hallmark movie about this?
I wish there were.
Let's do it.
Oh,
Do it.
yeah.
The
Do a trailer
the
for this
lambda.
Hallmark movie.
Yeah.
No. Lambda CDM universe is our benchmark model, and there has been some chatter recently about, we've talked on this
The
program about
intelligence
how there's some
agencies have been
problems
picking
in
up some
cosmology.
chatter.
Yeah, chatter. Well, we've talked about the Hubble tension, for
We have.
example, how this is a serious problem.
Keeps
In
me up at
addition,
nights.
some issues with, if one of the fundamental assumptions in cosmology is that if you look on big enough scales, the universe is
Big.
Uniform.
the same everywhere, right?
Yes.
Not big. It's
It's not big.
homogeneous and isotropic. It's the same everywhere.
Whoa.
If it's not, we're gonna, we have a serious problem. And so, but it turns out if it's not, you can kind of do away with the need for dark energy, and that's what these recent papers are about: is looking to see if maybe the data actually supports a non-homogeneous universe that doesn't require. So I don't know if that's better or worse. I don't know, but it doesn't require dark energy.
I don't like dark energy, if I can just
You don't like dark energy?
say that. I'm just going to take a stand.
Controversial.
Sponsor.
I don't like the idea that the universe is like blowing up, like
Yeah.
accelerating
Sure. Yeah.
out there. I don't like
I kind of agree with you on kind of a philosophical, because if dark energy really is a thing and it's the thing we think it is, then the universe is just going to keep expanding forever and keep accelerating its expansion forever. And that's a little bit frustrating.
It's very lonely making.
Also, here's the thing about astronomers. We like to, a lot of our models depend on these assumptions that everything's the same because, that's how you can't not assume that historically, right? You have to assume that,
otherwise you don't get anywhere.
You can't do the model kind of thing, right?
Right.
You go okay, you have to have some starting assumption.
Right.
And that's even that's at all scales, right? And when we observe planetary bodies, we say oh, well, it's doing this thing now. Clearly, we're not observing it at some special point in time.
Right.
It's always been doing this, but that's always wrong.
Right.
Almost always wrong. Always, if we're observing something,
it is a special time.
It's a special time.
It turns out more often,
something
frequently.
Things change all the time.
Yeah.
And so it's an interesting thing that we have this assumption that and I'm simplifying it, but that
yeah.
It's going to be homogeneous and isotropic. When at every scale we look at, it's that we can tell it's not.
Right.
Right. Well, I mean, yes and no. So obviously, originally, you're right. I mean, when Einstein first kind of proposed, well, I don't know, Einstein, but back in the 30s and stuff when we were talking about this, it was just an assumption.
I wasn't talking about it back in the 30s.
Make up. And it's called the cosmological principle, where we just made it up because if you don't do that, it's too complicated to write down the equations
you just
to do
go
anything
home.
with.
If you don't do that, you're just well, let's just go get
Your
a drink.
abacus cannot handle it.
Yeah.
Right.
However, in the years between then and now, we have mapped out structure in the universe, and it really does look remarkably homogeneous and isotropic so it's not,
Except
it's now no longer
it
just a philosophical assumption. It's based on a huge amount of data as well.
Sure.
There's a lot of data and it's more, but I think to Addie's point, it's we do see these because we talk about giant structures. That's one of the things it's astronomers discovered the new largest structure in the universe.
And we're not talking about alien megastructures.
Right, yeah, this is giant
Not this time.
balls and sheets of superclusters of galaxies and things like that are a non-trivial fraction of the size of the observable universe. And then we're it's okay. It's still enough smaller than the observable universe that we can still have our cosmological principle, right?
Yeah. And it's statistically robust so far. At least we think that it is homogeneous. But if it's not, then maybe we can do away with this. To be fair, I think this is a pretty nice suggestion, right? I mean, I'm with you.
Legitimate
dark
suggestion.
Energy is a weird thing that we don't know what it is, and it's another thing you have to explain.
Right.
And so it sucks to have it there, but the standard cosmological model has been successful at a lot of things, and so this thing is just looking at how fast supernova are moving away from us, but not looking at a bunch of the other things that our standard cosmological model does accurately describe, the what's the background radiation, the
cosmic microwave background.
And a bunch of other stuff on large scales. It does beautifully. We talked about simulations, when we simulate how the universe will go from its early stages to its late stages. When we plug in standard cosmological model, it ridiculously well reproduces what we see in the universe. So these ideas that do away with dark energy have a lot of work to do before you convince me that dark energy is not real.
All right. Well, we'll keep our fingers crossed, though.
Sure.
Okay. We talked about the fast spinning pulsar, 1.4 milliseconds to do one rotation for something that's 10 or 15, 20 kilometers across. Mm-hmm. What is the fastest measured rotation period for an asteroid? And I'm going to put air quotes around the word asteroid here for you.
Okay.
So what's the period of rotation fastest has been measured for a rock in space?
Yeah, it's some rock in space.
15 minutes.
15 minutes, says Jim Cooney.
7.
Addie's sticking with 7.
Yeah.
1 minute.
1 minute. Addie gets this since she's going unitless, as long as her units are seconds. Because
they were going to be minutes.
Or tenths of a second. The answer is 2
minutes.
seconds. So
really? Wow.
2 seconds.
Was it this big?
It was
Besides
that
a basketball?
big.
Yeah.
It was 1 meter across.
Oh.
Yeah.
Oh. How do we measure the rotational speed of that?
Where, who,
Well,
what, when?
Was it about to
I can
enter
answer
the
all
atmosphere?
these. Yeah. I can answer all these questions.
Do I get points? Plus
Yes.
1,000 points. Now I'm back to 0.
Okay. It impacted over Berlin in January 2024. It was discovered shortly before impact.
Sure.
And if it's rotating every couple of seconds, what did I say? 2 seconds?
2 seconds.
Well, they only have to observe it for like minutes, and you see a whole bunch of photometric oscillations of the light curve. So, yeah, they could measure the rotation of this thing. They saw it for a few hours before it impacted the atmosphere. There's another one that's still out there that's got a 3-second rotation period, if it makes you feel any better. That's like about maybe 5 or 10 meters across.
Oh.
Okay. So, and that one's, it's out there in space. It's a near Earth object. Now, let's consider the planets in our solar system.
I do consider those.
If you're on this equator of the Earth, the rotation of the Earth is carrying you around at a speed of about 1,000 miles an hour, roughly.
Okay.
Jupiter.
That way it was windy today?
No. Jupiter is the largest planet in the solar system, has the shortest day. So it's the planet on which you'd be moving the fastest at its equator.
Yep.
So how fast would you be moving on the equator of Jupiter? What planet has the slowest speed of rotation at the equator, and what is that speed? Let's do the slow one first. I think I may just tell you the answer for Jupiter because I don't want people trying to figure things out.
1% the speed of light.
That's still too fast. That's far too fast.
For the slowest one, are you saying?
No, for Jupiter.
For Jupiter. Yeah.
Slowest one I'm saying is Venus.
Venus.
Okay. And how fast? And what do you say? Which
Venus.
All right.
Yeah.
It's unanimous, and that's correct.
Yeah.
It's like a day.
But what's your speed if you're on the equator of Venus?
So that's like
5.
270 days or something like that. So it's going to be 200 and something times less than. So
Oh, he's doing math.
I know.
Yeah.
5 kilometers per second.
Yep.
Jim, is that what you're saying also?
Yeah.
And
I have an order of
4.
magnitude off.
3 kilometers per second.
yeah, you're all orders of magnitude off. And Addie, you should have stuck with 7. It's 6.5 kilometers per hour.
Oh, you said kilometer. Oh, that's what I said.
It's not. So that's slightly faster than a walking pace. Yeah, it's about 4 miles an hour or something like that.
Okay.
What's second slowest? You all were right on Venus. Second slowest would be?
Uranus? No.
Pluto.
Jim says Pluto.
The planet Pluto?
Yes,
Damn right.
Mercury.
Mars?
it's Mercury. Pluto's third.
Yeah.
Pluto's third. On Jupiter, the speed is 45,000 and some kilometers per hour, which is
I didn't
not
get to guess.
quite twice as fast as the International Space Station
Because its rotation
orbits the Earth.
is
It rotates once in 10 hours.
10 hours, yeah.
And it's big.
Yeah.
Yeah, so it's super fast. All right, let's see if we can nail the outro.
We got it.
All right.
We got it.
While it may have felt like spinning at the speed of light, whatever that means, it was just another episode of Walkabout the Galaxy.
Be sure to follow us on Instagram and YouTube. You can contact us at wtg@ucf.edu.
Our theme music was composed by Richard Jerusik. Production assistance is provided by Logan Basinger.
Thanks to our listeners in Southern California. Stay safe. I'm Audrey Martin.
I'm Jim Cooney.
I'm Addie Dove.
And I'm Josh Caldwell. We're the astroquarks signing off until the next episode of Walkabout the Galaxy.
Mwah.